Hello guys, welcome back to Pascal Iron YouTube channel. So today I'm going to take ionic equilibrium one shot. So let's start. So first of all, ionic equilibrium starts with ions. So basically ions comes from an electrolyte which may be strong or weak. Basically the strong electrolyte is the one which releases the ions easily, and weak electrolyte is the one which releases the ions and takes time to release. That's weak electrolyte, strong electrolyte. Strong electrolyte means we can take strong acids and strong bases, and weak electrolyte in the sense weak acids and weak bases. So first of all, how can we define an acid or base? Based on three theories, which is Arrhenius theory, Bronsted theory, and Lewis theory. According to Arrhenius theory, we can say that if any substance releases H plus ion in aqueous solution, then it termed to be an acid. It is an acid when it releases H plus ion in aqueous solution, and similarly it is a base if it releases OH minus ion in aqueous solution. But one exception is that we know that NH3 is a good base, but it does not release OH minus ion in aqueous solution, so it is not considered as an Arrhenius base, which is an exception for this thing. And remember, according to Arrhenius theory, H3O plus is stable than H plus ion in an aqueous solution, and also this H3O plus ion is present at high temperature. Whereas the multiples of it, like H4O9 plus, this is present in low temperature type, right? But out of these two, out of this and this is more stable. H3O plus ion is more stable. Okay. Now coming to Bronsted one. Bronsted one is like if you have a way, simple definition, H plus donor is called a base, and H plus acceptor is called the arrow reverse, which is acid, and this is base, right? So let's see, Bronsted is H plus donor is acid and H plus acceptor is base, irrespective of any solvent. Any solvent, this is true, but for this only aqueous solution. So for Bronsted, this is the case. So for example, if you take like Ha plus H2O changes into A minus, which is the conjugate base for it, and plus H3O plus ion, which is a conjugate acid for this thing, right? So here we define new terms called, if it is an acid, its conjugate base is removing H plus ion, and if it is a base, its conjugate acid is adding H plus ion. Correct? So in this way we have acid and its conjugate base, base and its conjugate acid. Here, if we have strong acid like HCl, if you have strong acid, then its conjugate base is going to be weak base. If you have a weak acid, its conjugate base is going to be strong. Similarly, vice versa for bases. If you take strong base, its conjugate acid should be weak. If you take a weak acid, weak base, its conjugate acid is going to be strong. Okay, this is about conjugate acid base concept. So now let's go with Lewis concept. As per the Lewis theory, electron pair acceptor is an acid, and electron pair donor is called a base, right? For example, if you take BF3 plus NH3, it will form BF3 NH3 adduct, right? Here NH3 has lone pairs and BF3 has vacant orbital, so it is donating the electrons like this. So this is a Lewis base and this is the Lewis acid, correct? Now this is forming Lewis acid base salt, which is also termed as adduct. Okay, this is also termed as adduct. So this is an example of Lewis acid. This is the concept of how the acids were defined, acid base, how they are defined. So guys, few examples of Lewis acids are BeCl2, BF3, and AlCl3, and so on. And we have D block elements CO plus 3, Fe plus 3, Mn plus 2, like that, and so on. And we also have, but remember one thing, Na plus and K plus are not Lewis acids because they do not have any vacant orbital. They are completely filled. They have helium configuration, sorry, neon configuration, right? So they do not come as Lewis acids. Remember that. And Lewis bases examples are this all halogen minus, like F minus, Cl minus, Br minus, I minus, and also having lone pairs H2O, NH3 base, and so on. So these are few examples of Lewis acid. Now, which is take a reaction like we'll take this basic reaction. This is an acid, right? HA. HA is some acid. plus H2O changes into A minus plus H3O plus ion, or H plus ion you can take. For simplicity, I'm going to take H plus ion. You can understand better. Okay, H plus ion. Now for this, as per chemical equilibrium, we can define a K equilibrium, right? Equilibrium constant, which is products concentration upon reactants concentration, correct? Which is H2O times HA. This is the what? Now this K equilibrium is due to the dissociation of which acid? This acid. Since it is dissociation of this acid, we can also term this as dissociation or ionization constant, a new constant Ka, which is equal to K equilibrium at that time. And now here it is A minus, which is a base ion, which is acid ion, right? This one here Kw. Kw in the sense H plus concentration times OH minus concentration is termed as Kw for ionization of water. Ionization of water. For water. Correct? Means for if H2O will dissociate as H plus plus OH minus, then if you write K equilibrium constant, here will be H plus into OH minus by H2O. That H plus into OH minus, we gave a new term called Kw upon concentration of H2O is equal to Ka for this one. And this is K equilibrium is Ka is this one, whereas Kw is for H2O. Here also we can define Kw because it is basically cation into anion concentration. So I can write it as Kw of HA. Like this I can write it. So this is the difference between K and Kw. K is directly total equilibrium, this one, whereas Kw is the H plus into OH minus concentration is equal to Kw for ionization for H2O. So don't it down. So guys, we have seen K and Kw, right? These are the things. Now, but one more conclusion we can make is that if the value of Ka, the ionization constant for a particular acid, if it is very large, too much in 10 raised to 6 like that, 10 raised to like that, then that this Ka is termed to be, means if it is very strong, then that acid, the ionization constant of that acid, particular acid HA, is a strong acid. We can term that strong acid because K is much large. It is easily dissociated. Means that HA plus H2 is converted into products very fast. In the sense, product concentration is so much. If numerator is so much, then we can term it as a strong acid because numerator we have H plus ion, right? So for strong acid, the concentration of H plus will be more. So you can H is much K is, if K is greater than so much, then it is strong acid, and if K is very less, then it is it's a base. Actually, it's not a strong acid; it's a weak acid, right? Because it is always try to go backward reaction, right? Because understand like this: have CH3COOH plus you have HCl changes to CH3COO. Let's take H2O better, you can understand easily. H2 CH3COO minus plus H plus H3O plus ion, right? Here we know that CH3COOH is a weak acid and this is a weak base, correct? Now CH3COO minus, it's a conjugate base will be very strong. So it's a strong conjugate base, it's a strong conjugate acid. We always know that strong acid and base will always react. It may be anything. So since these two are strong, these two will react and try to form a backward reaction. So the concentration of reactants will be more. Concentration of reactants more means concentration of denominator is more. So overall fraction is less. That's why K is less for weak acids. Got it? So now let's see pH scale. So guys, let's see pH scale. So pH scale, pH is defined to be, actually it is used for finding the strength of acids or bases as you know. But the definition of it is pH is equal to minus log of H plus concentration. I don't think everybody knows this. So now simple basic terms, if pH is greater than 7, then it is a base. Equal to 7, it's a neutral solution. And if it is less than 7, it's an acidic solution, provided at 25 degrees Celsius only. At 25 degrees Celsius only. And for why pH equal to 7 for water? Why? Because it is found to be experimental. P means concentration of H plus is equal to concentration of OH minus at equilibrium is found to be 10 raised to minus 7 molar at 25 degrees Celsius. So this is why at 25 degrees Celsius this was found. That's why we have taken 7 as a neutral number. Suppose it is 10 raised to minus 6 as a neutral at some other temperature, then we have to take in 6 as a neutral point. So it depends on the temperature too. The pH depends on the temperature. Okay. And one more thing is that Kw from this we can write as 10 raised to minus 14 because product of these two. So now pKw is equal to 14. So our pH scale is up to 14. Up to 14. Okay. Got it? If it is 10 raised to 6, 10 raised to 6, it will be 10 raised to 12. So up to 12 it would be. Depends on temperature. Temperature factor is quite important in pH. Right? So one more thing about is this. We have to know one important relations, like if H2O is there, it will dissociate into H plus and OH minus, and this is an endothermic reaction. So delta H is greater than 0. Okay. So if it is endothermic reaction, as we increase the temperature, the reaction goes forward. So dissociation increases. Alpha dissociation constant increases, which we are going to discuss in Austen dilution. I will tell now. So alpha increases. So concentration of H plus and concentration of OH minus dono increases, which implies pH decreases, pOH decreases because it is minus of log H plus, and pKw also similarly decreases. So these are things you have to know. This is an endothermic reaction and these things are going to happen. Now let's go with Ostwald's dilution. In this you can get few formulas, you have to remember those. So let's see them. So let's see Ostwald's dilution. According to Ostwald's dilution law, for example, if you take an acid HA, it will dissociate as A minus plus H plus. Correct? So initially that is assume it has concentration of C naught. Initially these are nothing at T equal to 0. Now at T equal to some equilibrium time, it will be C naught minus some X is removed. This is formed X, this is formed X as per chemical equilibrium. So now we are defining a new constant called alpha, the dissociation or ionization constant. That is Ka is different. This is a degree of dissociation factor, you can call it as. Okay. This alpha is degree of dissociation, right? It is how much the formed one by original one, correct? Formed one by original one. So we can replace this X to be alpha C naught. So from this you can write C naught into 1 minus alpha and C naught alpha, correct? So remember this, alpha equal to X by C naught, degree of dissociation. Degree of dissociation, correct? This thing. Now if you write K equilibrium, or which is Ka because it's an acid, so it is C naught square alpha square by C naught into 1 minus alpha. You cancel these two, C naught alpha square by 1 minus alpha, correct? Now as per the Ostwald's dilution law, when alpha is negligible, if alpha is less than 0.05 molar by alpha equal to this thing, if it is this was, then we can neglect the alpha in the denominator. So it becomes Ka equal to C naught times alpha square, which implies alpha equal to under root Ka by C naught. Got it? So now we have got the alpha. So now we can find the pH of the solution because C naught into alpha. We know C naught given and alpha is here. So we can replace this C naught alpha as root Ka in times C naught. Correct? So now we have Ka C naught. So we can find pH because we have H plus concentration, right? So I'm going to erase it now. So H plus concentration is root Ka times C naught. Now pH is equal to minus log of H plus. So Ka C naught whole raised to 1 by 2, which implies half of pKa minus, half of, you get, if I, one more thing is that I can replace Ka with log Ka, minus log Ka with pKa, and minus log C naught, which is minus log C naught. So it is half of pKa minus log C naught. Correct? So this is how you find the pH. Right? So this is the pH of the solution for this thing. If you have a base pKb minus log C naught for pOH. And one more thing I have forgot, I think pH plus pOH is equal to 14 is equal to pKw at 25 degrees Celsius. Okay. So you can easily find, if you have pH, you can find pOH. So this is about Ostwald's dilution law. Here dilution, you can use this thing. This is what Ostwald said. Right? This factor. So try to remember this formula and this formula. This one and this one, important, very important. And if you remember alpha, that's well and good. Alpha equal to root Ka by C naught, right? So these things are important from Maxwell's resolution. Now let us check common ion effect. So let's see common ion effect. So common ion effect is very simple actually. So if you have H2O, to dissociate, first of all, let's take some acid. So if you have some acid like HCl, in aqueous solution it will dissociate into H plus and Cl minus, right? Now suppose if it has a concentration initially C naught, removed, it will be C naught minus X, X and X, right? And in aqueous solution H2O is also there. It will also dissociate. H2O will dissociate into H plus OH minus, right? Initially it has some other concentration. Let's take some A naught 0 A naught minus Y, and this is Y. If you find the pH of the solution, you have two ions, H plus, this is the one source and this is the one source, right? You have two factors of influencing H plus. So this is a common ion effect. One ion is from this one, this one ion is from this one. This you find pH, have to take X plus Y and Y plus X because both are contributing as an H plus ion in this reaction. So for that, I have to take K equal to this into this by this into this by this, and you have to do math and you will get the answer. Basically, you have to take X plus Y and Y plus X. It's a very important point to note. This is about common ion effect. Any common ion effect questions, you have to do the same thing. Write X plus Y. If it is even this is same, you have to write X plus Y. Okay, this is about common ion effect. So guys, this is a list of strong bases, weak bases and weak acids. So BH and weak bases are NH3 pyridine, aniline, methylamine. Weak acids are CH3COH, formic acid and phosphoric acid. But remember, I think HF is not a strong acid, it's a weak acid. This is one of the most important point. HF is a weak acid. Okay, this you have to remember because it is also useful for salt hydrolysis and also for buffer solution. This especially this phosphoric acid and pH calculations failure to dry basic acid. So let's see pH calculations now. Now, if given 10 raised to minus 3 molar HCl solution is given, what is the pH of the solution? Remember, if HCl concentration given was greater than 10 raised to minus 6 molar, then you have to neglect common ion effect with water. Common ion effect with water. Okay, have to neglect common ion effect with water. If it is greater than 10 raised to minus 6, since it is greater, I can neglect. Now I can directly write pH equal to minus log of H plus, which is pH equal to 3. Directly I can write. But if it was 10 raised to minus 8, and if you write pH equal to 8, then it's wrong. Because we are neglecting H plus H2O from H plus because we are neglecting the common ion effect. So we have to consider the common ion effect. So now let's see how to calculate it. So we are going to find 10 raised to minus 8 molar concentration HCl, it's pH. So we are not going to neglect H2O concentration H plus. So basically HCl, right? HCl will dissociate as H plus plus Cl minus. Since the temperature is not mentioned, we are not supposed to take 10 raised to minus 7 molar as H plus concentration. So some X concentration. So X plus this thing, this X is due to from H2O. X is from H2O and this will be something, this Cl minus is not contributed for anything. So this is X plus 10 raised to minus 8. Now I'm going to write Kw. Kw equal to 10 raised H plus times OH minus concentration. Since I have taken H plus concentration as X, this will be X. So due to common effect, H plus concentration will be X plus 10 raised to minus 8 molar, which is equal to Kw, which is 10 raised to minus 40. Done. Find X. Once you find X, you can substitute here. You can directly get H plus concentration. Once you get H plus concentration, pH equal to minus log of H plus, which is X plus 10 raised to minus 8 molar. So solve this quadratic and get the answer. That's it. So simple question, but don't mark the pH equal to 8 as the answer for this one because common effect. Now weak acid and weak acid or weak base for anything. I have taken an example. Suppose HCN is 10 raised to minus 4 molar and K of HCN is 10 raised to minus 10. And they are asking to find pH. Simple. So before I have said alpha equal to root Ka by C naught, correct? K is 10 raised to minus 10 and C naught is 10 raised to minus 4, which is going to be 10 raised to minus 6 root 10 raised to minus 3. Since this is less than 0.05 molar, I can neglect the alpha. That's why I got this formula. I can use this formula because alpha is negligible there. Since it is less than 0.05, I can very well use it. So now we are going to find H plus constant. H plus equal to C naught into alpha, right? C naught is 10 raised to minus 4 times alpha is 10 raised to minus 3, which is 10 raised to minus 7. H plus combination this one. So pH equal to 7. Done. pH equal to 7, right? So guys, for weak monobasic acids, which implies like if you have a solution like this and having one acid like HA1 and another acid HA2 of K1, K2 as their dissociation constants, and let C1, C2 be their initial concentrations. Then you can directly find H plus concentration from this formula, which is K1 C1 plus K2 C2. Better to remember. And if you want to find alpha, the dissociation constants of for particular acid like HA1, then you can take K1 divided by this term K. Okay, now for alpha A2, similarly can write as K2 divided by this term root over K1 C1 plus K2 C2. So this is how you are going to deal with weak monobasic acids. So guys, we have di and tribasic acids. So these are examples of dibasic acids. Dibasic acids is the one which will release 2 H plus ions. So it will have two dissociation constants like Ka1 and Ka2, right? Dibasic acids, and similar tribasic acids have 3 H plus ions, which they'll have 3 dissociation constants. For example, if you want to write for H2CO3, for example, H2CO3 will dissociate with H2O as HCO3 minus ion plus H plus ion, right? Again, this will further dissociate as HCO3 minus will dissociate as CO32 minus plus H plus. So you will have Ka1 and Ka2. So these are the two things it's going to have. Similarly for H3PO3, we're going to have Ka1, Ka2, Ka3. You can deal with them. So coming to most important concept or most confusing concept, salt hydrolysis, right? Let's check it out. Salt hydrolysis is actually a very simple topic. So basically, salt hydrolysis. Suppose for example, in first case, a strong acid and a strong base. If you take for them, for example, HCl plus NaOH is going to form NaCl plus H2. This is a basic reaction, as you know. And remember, salt hydrolysis is applicable only when it is completely neutralized, which implies the concentration of HCl and NaOH at T equilibrium should be 0, 0. Then only salt hydrolysis concept is used, or else we will go with buffer solutions, right? I'm going to explain it also. So remember, when it is 0, 0, then only you can use this salt hydrolysis formula or concept. So you have HCl and NaOH. You can directly form completely, it will neutralize to form NaCl. So at 25 degrees Celsius for this thing, you can directly write pH equal to 7, especially for strong acids or strong bases. It is direct, straightforward. So the twist is here is for go with weak acid and a strong base. Weak acid and a strong base. For that, for example, weak acid CH3COOH plus strong base NaOH will form CH3COONA plus H2O. Correct? Now this is salt of weak acid and strong base. So that this generally this pH is going to be greater than 7, as we know. So for that we have the pH formula equal to half of pKw plus pKb plus pKa plus log C naught, means concentration of the salt. So this is the pH formula. Directly you can apply this and find the concentration of this one. So for example, we have 20 ml of this thing and 0.5 molar, 0.5 moles. This is 0.5, this is 0.5, completely dissociate. Then only you can use this formula, else this is going to form acidic buffer. Okay. So you have similarly have a weak strong acid and a weak base. We had a strong acid and a weak base. For example, you can take strong acid HCl, weak base NH4OH. So it will dissociate to form NH4Cl plus H2O, right? Now for this, pH is going to be less than 7, obvious. So now pH formula is equal to half of pKw minus pKa minus log C naught. Direct straightforward formula. Okay, apply this and get the answer. For salt hydrolysis, means this two concentration should be 0 at T equilibrium. This is important. So this is about salt hydrolysis. We have seen 3 cases. Now the 4th case is with amphoteric salts. So if amphoteric salts are given, but what is amphoteric basically? The salts which behaves as an acid as well as a base. So it means we have come from an, if you put in acidic medium, they behave as a base. If you put them in basic medium, they behave as an acid. So dual character. For amphoteric salts. So for that, they'll have Ka1 and Ka2, right? Means for acidic ionization Ka, for basic Kb, something sort of like. Then we can write pH equal to directly half of pKa1 plus pKa2 direct. So here NaHS is a amphoteric salt which will dissociate as Na plus H minus this thing, right? So for that we can directly write Pa. For this reaction it is Ka1 as a constant and Ka2 as a ionization constant. So you can directly write pH equal to this thing, this formula. But an important observation is that it is independent of the concentration of the salt. Independent of concentration of salt, correct? It do not depend upon the initial concentration, which is one of the key point of observation. So guys, now let's see buffer solutions. Basically, meaning of buffer is solutions which resist change in pH on adding small concentration of an acid or base, which will resist the change in pH. Like they will remain to be in one particular pH for some time, and after adding some few drops of an acid or base, suddenly the pH is going to change drastically. Those are buffer solutions. Basically, those are prepared by the incomplete titration, sorry, which is not equal concentration. If it is equal, then salt hydrolysis is going to take place. So it is incomplete titration. Let's see what are this. First of all, buffers are of 2 types. One is simple buffer, and next one is mixed buffer. Correct. So simple buffer is formed by weak acid and a weak base, salt, which is CH3COO NH4OH. NH4 we can take as. So this is one of the example of it. Now if you take mixed buffer, which is very important, which is acidic buffer and also basic buffer. There are 2 types of it. Mixed buffer is of 2 types, acidic and basic buffer. Acidic buffer is formed by weak acid and a strong base titration, and basic buffer is formed by weak base and a strong acid, or its conjugate. Basically you can take it as weak acid and its conjugate base, and strong acid and its conjugate base, like that. So in this, a weak acid should be excess. Anything one should be excess, so that it will dissociate. So this should be excess. Then you can directly form this buffer solutions. For example, to find this, you have to have incomplete amount of this concentration, not equal concentration. Then you will form a buffer. So let's see one example. So guys, let's see this example. CH2COH plus NaOH changes to CH2COO Na plus H2O, correct? So for this, suppose initial concentration is suppose C0, and initially for this concentration some X. C0 is not equal to for X, different, going to form buffer. So X, and initially this was 0 at T equilibrium. Suppose it is C0 minus X, and this is 0. Suppose it is completed, X minus X. Okay, so this is going to be X and this is going to be X. Since this is somewhat left out, again this will dissociate in water, correct? So it will form CH3COOH will dissociate as CH3COO minus plus H plus. So while contributing for pH, this will both will contribute. So this is going to be C0 minus X, and this is 0 0 at initially, and this is also going to form a salt which will increase its concentration. Suppose it was XS concentration, this is C0 minus some X minus S something, plus X it will be there, plus S it will be there, and this is some X concentration, S concentration. If you find X by solving them, you get as X equal to K times H plus by the salt concentration, which is S, salt concentration. So To find pH, we have direct formula. Use it for this thing. pH equal to pKa or pKb depending upon plus log of salt concentration divided by acid concentration. Directly you can apply this formula, no need to know the derivation for this. So pH equal to pKa plus log of salt upon acid. This is also known as Henderson's equation. This is also known as Henderson's equation. So they may ask in exam what is Henderson's equation, you can write this one. And if you want POH, take it as pKb upon base concentration. That's it. So this is about buffer, and yeah, this is about buffer. Now let's see buffer capacity. What is buffer capacity? The buffer capacity is nothing but denoted by the letter phi. So it is denoted by the letter phi or some eta, anything. So which is defined to be number of moles of acid or base added per liter of the solution, divided by change in pH of the solution. Generally by unit change in pH of the solution we take. So now phi is equal to number of moles of acid or base added per liter of the solution, divided by change in pH of the solution. Right, this is the formula for buffer capacity. So you can directly apply this formula, but remember it's per liter of the solution. Questions may confuse you. This buffer solutions. Now just now I have said buffer capacity equal to change in number of moles per liter by change in pH, correct? So this one important result is that, which is it is equal to 2.303 SA upon S plus A, which is S is nothing but number of moles of salt, number of moles of acid, So by using this formula, you can compare buffer capacities between two given concentration of two respective salts. Okay, so you can remember this result. So indicators basically define how the equivalence point is reached at what stage. Means they generally show the color. By changing color and red, you can identify. Those are indicators. For example, there are two types of indicators. One is acidic indicator and next one is basic indicator. So acidic indicator is, example is HPH, which is phenolphthalein, which is actually weak acid, and methyl orange, MEOH, which is a weak base. So these two indicators are used. So we have to know the important features of it. Means when you add a basic solution, you have a basic solution and you are adding phenolphthalein to it, so it will show a pink color. So in basic solution it will show pink color. In acidic solutions it will be colorless. So it will be colorless for acidic solutions and pink color for basic solutions, phenolphthalein. Coming to methyl orange, it will be red for acidic solutions and it will be yellow for basic solutions. So for this there are many indicators. Out of them, 4 indicators are very important. I will give a list here, you can see here. So out of these 4, you have to remember, out of several indicators, you have to remember these 4 CTR values, means color transition ranges, as shown in the figure, the photo. So come back. Now this now the HPH we have. Let's take this example. Now phenolphthalein we have, right? In phenolphthalein, if you add into some solution, it will dissociate as H plus plus pH minus, correct? Now if you write K equilibrium constant, which is going to be H plus concentration times pH minus concentration divided by HPH concentration, phenolphthalein concentration. So from that I can write H plus equal to, let this be dissociation constant of indicator. So H plus is equal to KIN times HPH by pH minus concentration. Since I got H plus, I have found pH also. pH equal to minus log of this thing, which is going to be pKin plus log of HPS concentration, sorry, log of salt upon acid, right? Similar formula it would be there upon HPH. This is the formula you are going to get for pH, for phenolphthalein indicator. Similarly, by extension, we can write pH equal to pK indicator using methyl orange, which is going to be log of Me plus 2, Me plus concentration divided by methyl, means methyl concentration divided by methyl orange concentration, right? You can directly find pH of it. Means nothing but K ionized form by K unionized form. In simple language, if you want to say. So this is all about indicators. So we have too many things about indicators, like the curves, titration curves we are going to see now. So guys, these are all about indicators. Now first of all, what is the criteria to choose a particular indicator? First of all, the CTR range or the pH range of that indicator should lie in the steep of the curve of the titration, which I am going to explain now. And also one more thing is that pH, the equivalence point, should lie between the range of the particular indicator. Range of the pH of the indicator for methyl orange it is 3.1 to 4.4, right? Between that range, the pH of the equivalence point should lie. Then you can use that suitable indicator. So by experimenting, we have found strong acid and strong base. If you use both methyl orange and phenolphthalein are good. Both are good. For weak acid and weak acid and a strong base, phenolphthalein is good. Why phenolphthalein? Since a strong base, by drawing this titration curve, it is going to be, since consider this as a titration of, we have weak acid. Suppose the solution is containing CH3COH, and by titration or by the burette, I'm going to add strong base like NaOH by drop. So this is CH3COH. This is a weak acid. So initially it is going to be some 6 pH equal 6, something like that. Suppose this point is some 6. Now on adding NaOH, the pH will increase. So this is a pH versus volume of NaOH added. Correct? So it is starting from here, it will go like this. A particular point it will be like this. So this is a region where equivalence point is observed, where the curve is somewhat steep enough, like this. This is the point where equivalence is observed, this volume of ml, and this is a particular concentration where pH where equivalence is observed, where the curve is steep enough, as you can see few examples here. Got it? Right. Now coming to weak base and strong acid. For weak base and strong acid, we go with methyl orange as a suitable indicator. Remember this thing. So coming to double indicated titrations. The double indicated titrations are the one in which if you have something like HCl as 0.1 molar and Na2CO3 as this data is given. In aqueous solution, Na2CO3 or H2CO3 basically, H2CO3 will dissociate as HCO3 minus ion plus H plus, correct? And HCO3 minus will dissociate as CO3 2 minus plus H plus, right? So it will dissociate two ways. So it will have K1, K2, two equivalence points. So the titration curve is going to be, I'm going to erase this part. So now the titration curve is going to be like this. So in this case, I'm adding HCl to this base. So initially, since it's a base, initially the pH is going to be greater than 7. So it is somewhere, assume it as 10. Somewhere, I don't know exactly. So it will come like this. As adding HCl, pH is going to decrease. So it will be slowly coming here. And it is going to be like this. One curve, and it will come like this, and again one more steep. This is first half equivalence point. This is second half equivalence point, like this, by volume of HCl added by pH. One equivalence point and second equivalence point. So by observation, for first equivalence point, phenolphthalein is used because its pH range is from 8.1 to 10.4. And for second equivalence point, clearly we can use methyl orange is useful because methyl orange is from 3.1 to 4.4. So remember those values I have given in the table before only. So these are the things you have to remember, right? By observation you can tell this, and you can directly find pH at equivalence point or the volume at the equivalence point by using N1V1 equal to N2V2. We have these two. You can find the volume at the equivalence point. Once you get the volume, pH equal to that buffer solution formula, pKa plus log of salt upon acid. Done. This is how we are going to find pH at equivalence point, right? So guys, for hydrolysis of salt involving strong acid, strong conjugate acid and amphoteric ion, for example NH4CO3 and NH4S, we are going to directly use this formula H plus equal to Ka1 Kw by Kb minus Ka1 Ka2, right? It maybe it depends on your remembering skills, not most but useful. And so let's see iodometric titrations and dimetric titrations. Iodometric titrations involve two steps. They involve two steps, which implies first of all I2 is released during one reaction. That I2 released one is used, it is titrated with another part of the reaction. For example, if you take this example, determination of copper to sulfate using thiosulfate, using iodine basically. So Cu2 plus copper sulfate with iodine forms Cui. In this I2 is released. Now this I2 is reacted with hypo, right? Now this is going to form I minus. So by knowing the number of moles of this and this, you can direct hypo, how much hypo is used, we can directly calculate the determination of this copper to sulfate. This comes under iodometric titration because it involves two steps, releasing of this and using with some titrating with something, anything. So basically in this starch is used because starch will form a colored complex with I2 which is used as basically visible, right? I2 is released. That's why starch is used for iodometric titrations, remember it. Now coming to iodometric titrations involve a single step. A single step in the sense I2 is used directly and directly will get this product. So this is nothing but ascorbic acid is determined with iodine, right? Ascorbic acid is determined with iodine. Directly you will get this one, right? So this is for dimetric. Di means 1, do means 2. You can remember in this way. So guys, this is all for this video. I hope you like this one shot. So please do subscribe for Pascal Aryan YouTube channel. In the next videos, I'm gonna upload advanced PYQs. So please do subscribe for this channel and bye bye now.